Perfect.
Amazing. Well, thanks everyone for having me in this workshop. I'm very excited to be here. And I want to give you some thoughts that I've been having recently, I would say, but actually for a while also, on what is the role of scene, how can scene help us be not just more general, but also more precise. So with that said, I always keep in mind this, right? If you go into a factory that has a lot of robots are going to look like this. So they're going to look very nice, very capable, very precise. And this is great, but it comes with a problem actually. If you go these days into a factory, what happens is you have one robot doing one job, and that means that you don't have flexibility. And this is a real problem because if you are a small, medium company that wants to go into automation, into assembly, how do you do that if you cannot afford to spend all the money that it takes to get those robots to just do one robot per job? So instead, I always like to have the analogy of I would like my robot to be like my phone. Because if you think about your phone can do a lot of things. But not just that, if you think about it, we used to have a lot of devices to do what your phone does today. But not just that, your phone probably does it even better than what we used to have before. And I think that's actually what we want. We want to have this performance. So how do we get there? Well, I think that's what we want for our robot. We want a robot that can do a lot of things, but they can do them with a skill. It's really capable. So with that in mind, when I think about the research that I've been doing, I think about these two axes. One of them is generality. We want robots to be flexible, adaptable. On the other one, we want them to be precise because we will never be happy with a robot that every now and then fails, does something wrong, breaks our mark. And I think the idea is how do we go through this path? How do we keep in mind both axes when we do research? So I will talk about some things briefly, but basically this is some of the work I've been doing recently that I think moves a bit into this spectrum to kind of keep the tension between the two axes to make progress. And I'm going to start with this one, which we call simple, which is going to be more on the axis of let's be very precise, but maybe in terms of generality, let's not think too much about this. We're going to get some generality, but just across objects. So this is how it's going to look like. We're going to have this robot. This is again kind of an assembly task where what we want to have is these objects precisely placed into these positions. So in the video that I'm going to show you in a second, you're going to see how this object needs to go into this position. And the robot needs to be able to reason about that. And it's not trivial because depending on how you grasp it, how are you going to place it, sometimes you need to regrasp. So if you pay attention, you're going to see how the robot needs to identify the object, do this regrasp, and precisely place it into the location. So how did we solve this problem? This is work that we did at MIT. I just want to give you a sense of how we think about precise pick and place. The idea is that the robot needs to be able to pick the object, that's grasping. We know how to do that. But it also needs to understand what is the object. So we are going to be doing localization. And from there, we're going to just be, which basically means what is the object. And finally, you're going to place it. And the place is precise. So something that you need to keep in mind is that sometimes in order to get into that position, you will need to do a regrasp. And why is this problem important? Because this actually is like assembling a kit. And if you ever go to a company, kits are everywhere. It's amazing. They have all these pieces into this exact location. And once you have assembled the kit, it just goes into a machine because now you know exactly where the objects are. And if you go into industry, you have people assembling the kits. And as you will see here, the person is just placing, understanding, regrasping, and doing exactly the thing that what our robots do. So now the question is, how do we get better? I'm not going to go into all the details. This is what that was published actually recently in Science Robotics. But here's a bit of what we want to be doing and some of the components that this work has. One of them is the generality that we've been able to show is that we use the object shape. That's something to keep in mind, although we can relax a bit this assumption. But then we can do zero shots into real for any object as long as we have the object model. And the components that we use, the precision comes through two things. One of them is visual tactile perception. We not only have vision, we also have tactile. Tactile refines our understanding of the pose of the object, and we have shown in the paper that tactile helps. Of course, vision helps for sure. And we also do some task-aware planning. If you want to reason about how to move the object, you need to have a planning, a task awareness that understands what is the task, not just, am I going to succeed at a grasp, for instance. So with that said, I'm going to go in more into the details. So how this works is you take a depth image that looks something like this, and now you want to be able to say, in this object, where should I be grasping? So what we did here was just grasp sampling. That is something that actually works pretty well off the shelf. And then we also do pose estimation. We actually go into the details into the paper on how we do that. And from there, the next thing is, which is the grasp that I want to do, right? There is all these options, which one is best? And when you want to think about grasp sampling, you want to think about a few things. Not just that the grasp is going to succeed again, but also observability. What is observability? Observability means if I put my fingers here, will I be able to get some tactile information that will give us even more information of what is the object? Maybe this is not so good, and this one is the one that gives me the most, it gives me some features that I can really use to identify. And finally, simple placements, meaning if I need to end up placing this precisely, what is the right set of motions that I will need? Can I simplify those to make my manipulation easier? So with that said, now you're just going to select the best one, get the tactile image. This is a gel site type sensor that gives us this tactile information. And finally, you can combine this visual and tactile to get an updated pose estimation. And from there, we compute motion planning. This is inverse kinematics, something that we can do just kind of a simple graph approach onto which are the regrasps that we need to do for this task. This is just to show you a video of how this is working. Again, the graph sampling is happening. We identify the graph that is best. And once we perform it, we're going to be able to get, again, this tactile information that is going to show data. That actually is very indicative for this object, even though it's hard to see. That's very useful, so we can refine the position of the object. And finally, in this case, it computes and it needs to do one regrasp in order to do this insertion here, this placement of the object. The placement is very precise. It's on the order of 1 millimeter or less. So it's actually a complicated task to solve. But it's what we want, right? If we want to assemble those kits for industry. And the thing that was exciting is that all these components that I've been talking about, we just learn them in simulation, and we don't need any real data. So for any new object, as long as we have the object shape, we can just do all this approach and get performance. So finally, I think I'm just going to close this project. We got different experiments. We got pretty good successes across different objects, not for everyone. If you go into the paper, we describe what happens in those cases. Tactile helps, and this is into real, and I'm just going to show you this video, which I find satisfying. You're going to see the regrasp. For many of the objects, actually, you can do it without any regrasps. Oh, no, this is just showing one. Okay. Sorry, I don't have the full video in here. It does everything. That's it. So with that said, then I move into Google Deepmind. And then you know that at Google, they really think at the scale, at generality, lots of data. So this is some of the work that we did, Robocat. I'm not going to go into the details because this is not assembly. This is about generality. But this is a large team that did this. And the idea was, can we have a big model that can do a lot of tasks? And the way we solved this was through a cycle. And this is what I care about right now for you, which this cycle is about. We're going to have a lot of people collecting some data. We're going to take this data. We're going to improve our model with it. Our robots are going to be able to collect more data on these new tasks. And that's going to go into a bigger data set of data. It's all about data. And then we keep on going, right? But the key component of this is that the bottleneck is actually you need people collecting data, teleoperations, basically. And this is something that you can try to do at the scale if you're Google, but even then, it's not efficient. And this is probably not what we want to do every time, lots of time for every task, lots of data. So I think this is a bottleneck. So we're thinking, how can we do this a bit better? How can we lower the requirements of how much real data we need? And that is where we thought about DemoStar. And DemoStar now is going to be more of a precision and simulation and generality coming a bit together. So what is it about? Demonstration is auto-curriculum model. So we're going to talk about reinforcement learning, which I think for assembly feels like, wow. But the idea is that we're going to ground it with demonstrations from humans that are going to be recorded in simulation. And that's going to make the behaviors to actually be much nicer, but still optimal in the sense of reinforcement learning is going to give us solutions that are more efficient, more optimal in a given sense. This is, again, work from a lot of people. And again, the goal is I want to find a simple and a scalable solution in simulation. I want to use simulation. I want to generate trajectories that are kind of behaviors that are transferable to sim, because all we care is, transferable to real. All we care is real. Sim is good if it works, but that's not valuable. We carry things that work in real. And optimal again, because if you ever done teleoperation is slow. And actually, that's the way for us to get something that is better with reinforcement learning. And again, real is the most important thing. So I'm just going to give you a sense of how this works. This we have been able to transfer into an arm with a hand with 3 fingers. So this is a complex embodiment, 18 degrees of freedom. And here you have, I'm just showing you the results, the comparison between simulation and real world. And it works, okay, the geek is just playing again. It works quite well. Here, if you pay close attention, it does a reorientation of the connector, and then it's able to put it precisely insert into data. So this is kind of what we want to shift with Demostar, right? Now you go from simulation, you transfer it, in this case, 0 shot, and you're still getting performance and behaviors that are nice. So how are we doing that? First of all, how hard is to get Demostar to work? For a given task, all you need is actually sparse rewards, no dense rewards. You just need a success detector, is this working, yes or no? And a few scene demonstrations. A few can be 1, can be 5. It's not 100. It's really very limited demonstrations in sim. And the thing that we like a lot is that demonstrations can be anything. They can be extremely bad. They can come from a teleoperation that is not garbage. Like for the hand, I'm going to say what is informative, and then with the reinforcement learning, very simple MPO. With the important thing again is we're going to use a reinforcement learning, but the exploration comes from informative states. And this is a bit hard to explain, but me show you a video, just some animation of how we do it. This is the task that I want to solve right now. You have this cup, you want to put it upright, and then put the screwdriver inside. Don't ask me why. We decided to go for this task. And the way that this works, the curriculum works, is the following. This is to access. On this side, you're going to see where you're in the demonstration, right? If you're at 100%, you're at the end of the demonstration. You have almost completed the task. And here, just like policy updates, how much you are doing the training, right? So when you're almost done, you can be in a state where the screwdriver is almost inside the cup. So that is a state. All the policy needs to learn is just drop the object. And then as learning progresses, learning from states that are more and more informative. So again, easy to have, from the start being almost completed to being almost solved. And as the learning progresses, you're kind of seeing these states during learning. The idea is that you already know how to solve this state, you're not going to keep on seeing it. You're just going to be going in the learning to a state that are more informative. And now, what it means informative for us, how is that? That means in practice, it means that if in a state you always succeed, it's not informative. You already know how to do it. If you always fail from that state, it's not useful. You don't know how to do it. You want a state that we call zero variance. You want to filter states that have zero variance. You only want to learn from states that you sometimes succeed and sometimes fails. Those are the priority frontier. Those are the ones where you really can learn, and this is how we can guide the learning. Just focus on the states where there is informative information. And I'm just gonna finish with some key results. So far, we've been able to master all the tasks. As long as we have a demonstration really well. It shows this is the red and screwing. Again, the behaviors are not nice given the complexity of the embodiment. Um, we don't need much to add a new task, spare rewards in a few demonstrations. New embodiments, this is ongoing work, but this is like the alohas. This behavior is much, we made it to be slow, but it's very nice. This one is an assembly that is extremely fast. Again, many times faster than the demonstrations that we collected. We also have shown some results also for this embodiment, seem to real, but this is again work in progress. And finally, this is what I like, because of the way we are learning, this results in very smooth and consistent behaviors. This is just an overlap. And as you can see, the policies learn to just do one motion, kind of. And I think that's why there is this unimodality that is much easier to learn in sim and then to transfer into real. So with that said, I'm about to conclude. All I want to say is that, of course, there is a lot of work left to do. And some of the things that I am thinking, and I would like people here to think is, what is the role of sim to real? How can we do code training, not just rely on real data? I think that's very important for us to scale and be precise. Sim evaluations, that just means how do we use this sim to make sure that our real models really perform, like the digital twin idea, but how do we keep exploiting that? Combining RLM behavioral cloning or teleoperations from real, that's I think is a big problem. I don't think we have a solution because these are the data from here comes from very different distributions. So how do we fix it? It's not an obvious one. And of course, adaptation, right? If you have a very good model and I just give you a lot of more things to talk about. And with that, I'm done. Thanks everyone. And if you have any questions, I think now is the time.
Thanks for the very nice talk. I especially like to go like reverse, like this idea of like assembly by disassembly. Like I just was wondering, like, how does the algorithm decide when to change like the initial state distribution? Like, how do you decide when you basically want to learn the next phase of the process?
So this all happens automatically, and the reason why this happens automatically is because you visit the demonstration, let's say, from the beginning to the end. So if at some point you find a state that is informative, meaning again that sometimes you fail, sometimes you succeed, you're going to focus on that one. You're not going to keep on going, right? So that means at the end of the demonstration, when things are even more solved, you're not going to be looking at. And that's the way in which the curriculum happens on its own. So because the first thing that you try is, let's try any initial condition. Let's just sample an initial condition from my environment where the object is somewhere, random positions. If I can already solve that, the approach is not even going to look at the demonstrations because it can already center on initial conditions. If you cannot do a random initial condition from the environment, then it's going to start looking into the demonstrations from the hardest states where the task is almost not solved to the states where it's more and more solved. And this is how on its own, until it finds this kind of informative stage where it can learn from, it just kind of keeps on exploring, but through the demonstrations. And because we're using demonstrations, again, we're guiding the behaviors to be nicer than just kind of RL usual exploration.
But like maybe just one follow-up. So is it like a lookup table, or like how do you capture like this initial state distribution, or is it like a learned neural network that tries to map from initial state to like task success percentage?
No, in this case, so the initial distribution of the task, it just basically put the object in any configuration, right? And then from there, you have, let's say, 5 demonstrations. So basically, you select one of those demonstrations, and you go through it, through all the states of it. Another important thing is that we don't use the actions. We only use the states from these demonstrations. And then again, at some point, you're going to find one state that is informative. And that's how implicitly you're building these demonstrations of a state that you're learning from. As you keep on learning, at which point you're going to find a state that is informative is going to come sooner and sooner. So that meaning that the task is less and less solved, but you're still able to find cases where you can solve it. So it all happens on its own. We don't have to do anything that is very tailored for any task or anything. It just happens on its own. Yeah.
How much efforts were put into the simulation building, because it's often very metaphylist task, and from the experience, would we see that it's often easy to program the robot directly to perform the task than model the simulation?
Actually, for some of these tasks, you wouldn't be able to hard code it. It would be very hard, I think. Especially the ones where there's 5 objects that don't need to be placed precisely, and or they're not involved, where you need to do the matching. The matching is actually one of the hardest parts in data. I mean, I'm sure if you put enough effort, you can do it. But in this case, and also remember that at Google Deepmind, we have Mujoko people. We have the Mujoko team. So for us, the most important thing is, do we have assets? Do we have objects? Are those objects reasonable in terms of the physics? And this is something that we can actually make it happen. And then the reward is very simple, because the reward usually is like, is this object in this position relative to another one? Is this object inside this other one? So we just have kind of modular rewards that we can just keep on composing. So the reward writing, because it's a sparse, it's also very simple. And then that's kind of what you need, right? You just put the objects into the environment, you just put the reward, and then you just use some teleoperation device to collect. And as I showed you before, in this case, even with the space nav, which is something super simple, we can collect those demonstrations. For the Alohas, you can use Jealous, and that you just plug into your computer, your teleop device, and you just do those. And usually that takes us like 10 minutes, 30 minutes for someone that already knows how to use the teleoperation device. So actually onboarding new tasks is fairly nice. There is ways to do it better and better. And I think right now our biggest bottleneck is just, getting the assets, getting the objects, putting them in data, and writing the rewards, which is not too bad, I would say. And we are looking into that for sure, because again, this is a way to collect a lot of good data.
Just one comment on that. So you said that some of the tasks are not even possible, but it's possible. So within finite time, within 1 day or so, we have done it in our lab to program this task by hand, just for demos, of course.
Yeah.
It's possible, and then you have to weigh between modeling your task and directly programming tasks itself.
But there is one, if I understand this correctly, there's maybe one way of challenging this, which is that here we're using RL for the good and the bad, right? And the good is that you can actually optimize, right? If you manually just kind of hard code the task, this is your baseline, right? You're not going to improve over this. In here, if we don't like the behavior, we can actually modulate a bit the RL algorithm if we need it to solve it in a way that we think is more the behavior that we want to obtain. Or in another way, we could just say, okay, I would like to have this other behavior, so let me collect a different demonstration that shows the behavior that I want the RL to learn from. So this, I think, some extra modularity that you have this approach that hard coding is not going to give you.
Sorry, due to time constraints, I suggest moving into discussion to offline. Let's
I think
this
it's the only way.